Alright guys, in this video we're going to talk about section 8.3 hypothesis test for population mean. So I think if you have good understanding on 8.2 and 8.1, 8.3 should be very straightforward for you. Actually most of we're gonna see in this section we have seen it in the previous sections like 7.2 or 8.2, something like that. So first of all, let's start with a little quick review on the t-distribution to test hypothesis regarding the population mean assuming the population standard deviation is unknown. We use the t-distribution rather than the z-distribution when we replace the population standard deviation sigma with the simple standard deviation s. So this thing as what we went over in the section 7.2, this whole thing follows t-distribution with degrees freedom at -1. Okay. The reason why this happens is because we use the simple standard deviation instead of the population standard deviation. And we know that the simple standard deviation itself is a variable, which means it brings more variability into the distribution, which makes it more unstable. So once this is clear, let's just take a quick review on the properties of t-distribution. So because we have seen this before, I think I would just read it over for quick. Number one, the t-distribution is different for different degrees of freedom. Okay, so the different values of n, and just keep the idea in your mind, degrees of freedom is equal to the sample size -1. Number two, the t-distribution is centered at a 0 and the symmetry about 0. And then number three, the area end of the curve is 1 because of symmetry. The area end of the curve to the right of 0 equals the area end of the curve to the left of 0 equals 1/2. Number four, as t increases or decreases without bound, the graph approaches but never equals 0. Okay. Number five, the area in the tails of t-distribution is little greater than the area in the tails of a standard normal distribution because using the simple standard deviation little s as an estimate of the population standard deviation sigma introduces more variability to the t-statistic. So as what I just mentioned, the simple because different samples will probably give us different simple standard deviation. So which means the simple standard deviation itself is changeable. It changes. The simple standard deviation itself changes. Okay, which means the simple standard deviation itself is a variable. That means this brings more variability to the distribution, which makes the tails of the t-distribution longer than the tails of a standard normal distribution. The number 6, as the sample size n increases, the density curve of t gets closer to the standard normal density curve. This result occurs because as the sample size increases, the value of the sample standard deviation little s get closer to the value of the population standard deviation sigma by the law of large numbers. So that means the sample standard deviation s is getting closer to the population standard deviation sigma as n goes to infinity, which means the t distribution is getting close to the z distribution as n is increasing or goes to infinity. Okay, and we see a graph in the lecture video of 7.2, I guess. I think there is a slide showing us that when the sample size n getting larger and larger, the t curve is getting closer to the normal curve. All right, let's take a look at the testing hypothesis regarding the population mean. To test the hypothesis regarding the population mean, we use the following steps provided. Number one, the sample is obtained using simple random sampling. So technically, this condition is always satisfied in the problems we're gonna see in this class. The sample, number two, the sample has no outliers, and the population from which the sample is drawn is normally distributed, or the sample size n is large. So we gotta check those two conditions, or we just need to guarantee only one of them is only one of them is satisfied. Either the sample size n is greater than 40, or the sample is drawn from a normally distributed population. Okay. If sample size n is greater than 40, we don't have to worry about the distribution of the population. But if the sample size is less than or equal to 40, so we need to check if this sample is drawn from a normally distributed population. Okay. Pretty much most problems you see in this class will satisfy either this one or this one. Okay, but you need to check it. Number 3, the sample values are independent of each other. So step 1, very similar to the hypothesis test for the population proportion. Step 1, we want to determine the non-alternative hypothesis. So we're gonna have 3 different kind of tests: two-tailed, left-tailed, and right-tailed. So same thing. The non-hypothesis is always a statement containing the equality. So it's going to be equal to the mu is equal to mu sub 0. So the value of mu sub 0 is always given in the problem. Now, of course, if it's two-tailed test, we're going to have mu is not equal to mu sub 0. For the alternative, if it's left-tailed test, we're going to have mu is less than mu sub 0 for the alternative, and we're going to have mu is greater than mu sub 0 for the alternative if it's a right-tailed test. Assume mu sub 0 is assume the value of the population mean, so which is given in the problem, and that's why we're doing the hypothesis testing, right? Step 2, select a level of significance alpha depending on the seriousness of making type 1 error, and sometimes it's not given directly, so we're going to have alpha is equal to 1 minus the level of confidence. Okay, so the problem will give you either the value of alpha directly or give you the level of confidence. If the problem gives you the level of confidence, subtract that from 1 to get the value of alpha. And then step 3, p-value. Of course, p-value. And in this video, I'm gonna show you how to calculate the p-value by hand, or how to get the p-value from the t-table, of course, because we're talking about the t-distribution over here. And then I'm gonna make a separate video to show you how to find the p-value from the calculator. Okay. Now we know that I have to do this again. We know for the standardization, technically we have z is equal to x. I just want to mention this again, that the reason why I keep writing down this formula again and again is because this is super important for statistics. So z is equal to x minus mu over sigma. This is called a standardization. And just like always, so just the random variable minus the expected value of the random variable divided by the standard deviation of random variable will give you standardization, which is a standard normal distribution with mean 0, variance is 1. So since we know that the expected value of x bar is going to be equal to the population mean mu, so we proved this, I think, in the lecture video of 6.1, and I will say the variance of x bar is equal to the sigma square, which is the population standard deviation, over square root of n, and then of course the standard deviation of x bar would be equal to the square root of variance, which is a sigma over square root of n. And of course, if we know the population standard deviation, the things will be easier, right? We know that x bar minus mu divided by sigma over square root of n, this would be equal to z. This would be equal to z. If we know the population standard deviation, things gonna be easier. We just need to do the standard normal distribution. But the problem is that if the problem does not give you the population standard deviation, we are not able to find it if we don't know the population mean. Okay, so what we're doing here, we're gonna use the simple standard deviation. So x bar minus mu divided by the little s over square root of n. So we're going to replace the population standard deviation with the simple standard deviation. But as what we just mentioned at the very beginning of this lecture, we know that this follows a t-distribution. So this is the test statistic, t sub 0. Once again, the reason why we got t over here is because we use a simple standard deviation over here. Okay, and this is the test statistic, which follows the t-distribution with a -1 degrees of freedom. Okay, so degrees of freedom t-distribution is always a -1. So this the whole thing here is also called a standardization. Okay, but this is after the standardization, you will have t-distribution over here instead of a standard normal distribution, because we don't know the value of the population standard deviation, so we just use the simple standard deviation to replace the population standard deviation to give us a t here. Okay, I wish this makes sense to you. And then we just need to go ahead to use the a t-table to find the p-value. Okay, now let's take a look at first of all, let's take a look at how to find the p-value with the test statistic t sub 0. So once again, so if it's two-tailed test, this is actually very similar to the hypothesis test for population proportion. The only difference that we use t instead of z here, because it follows the standardization follows t distribution instead of standard normal distribution. Now, if it's two-tailed test, that means that the population mean could be either less than mu is not equal to mu sub 0. So this is the this is the alternative hypothesis. This is an alternative hypothesis of a two-tailed test. So this means that mu is less than mu sub 0. Oh, I'm sorry. Less than mu sub 0, or mu is or mu is greater than mu sub 0. Okay, it could be on the left hand side of mu sub 0, or it could be on the right hand side of mu sub 0, and that's why we had those two tails over here. That's why we have the sum of the area in the tails in the two tails is equal to the p-value. And we know that the t-curve is symmetry as well, so the area of those two tails would be equal to 2 times the probability of this one tail. So which means the probability would be, the p-value would be equal to 2 times the probability that t is greater than absolute value of t sub 0. The reason why we put the absolute value over here is to guarantee this number is positive. Okay. Now, if it's left-tail test, of course, the p-value is going to be equal to the probability t is less than t sub 0. And similarly, if it's right-tail test, the p-value is going to be equal to the probability t is greater than t sub 0. Okay, this is once again very similar to the hypothesis test for the population proportion, and the only difference is that we're using t instead of z because the standardization follows the t distribution. Alright, our technology, of course, we can find the p-value from the calculator directly. I'm gonna make a separate video for that. And then once we get the p-value, we just compare the p-value with the alpha. If p-value is less than alpha, reject non-hypothesis. This is the same thing as what we did for the hypothesis test for the population proportion. Okay. And then after comparing the p-value with alpha, you make a stated conclusion, either reject non-hypothesis or fail to reject non-hypothesis. Okay, so the procedure is robust, which means that the minor departures from the normality will not adversely affect the results of the test. However, for our small samples, n is less than or equal to 40, if the data have outliers, the procedure should not be used. So that's why I mentioned at the very beginning when we talking about the conditions. So we get to check the conditions if either n is greater than 40. Greater than 40? N is greater than 40, or n is less than or equal to 40, and the population is normally distributed. Okay, either condition 1 or condition 2 is satisfied. Okay, I just want to let you know that pretty much all the problems you will see in this class will satisfy either condition 1 or condition 2. You don't have to worry about that too much. But technically, we should check those two conditions. Okay. All right, so once everything is clear, let's just take a look at the examples here. I think the procedures are super similar to the procedures we saw in the previous two lecture videos. Now let's take a look at this example here. We have assumed the resting metabolic rate RMR of healthy mouse in complete silence is 5710 kJ per day. Researchers measured the RMR of 45 healthy mouse who are listening to calm classical music and found their mean RMR to be 5708.07 with a standard deviation 992.05. At the alpha is equal to 0.05 level of significance, is there evidence to conclude that the mean RMR of mouse listening to calm classical music is different than this 5710? So if we want to conduct this hypothesis testing, first of all, we want to set up the known and the alternate hypothesis. So the known hypothesis would be mu is equal to mu sub 0. What's the value of mu sub 0? Which is given here, right? 5710. And then let me put the verses here. Versus the alternative mu is what counter test we're doing here. So since we want to make sure if it's different than 5710, so this is two-tailed test. So we're gonna have mu is not equal to 5710 over here. And then we want to select the alpha, which is given 0.05, and then we want to calculate the test statistic. T sub 0 is equal to, what is it? It's gonna be the x, I'm sorry about that. It's gonna be x bar minus mu sub 0 divided by the sample standard deviation over square root of n. So of course x bar is 5708.07. I think it might be a good idea to write it down here. 5708.07 minus x bar, which is 5710, divided by the sample standard deviation, which is given here, 992.05, divided by square root of n, square root of 45, right? So if you type this whole thing in a calculator, you will get something. I will just go ahead to copy the answer from the solutions, okay? So this is something, is approximately negative 0.013. Okay, negative 0.013. All right, so the p-value would be equal to, so since we are doing a two-tailed test, if it's two-tailed test, p-value would be equal to 2 times the probability of t is greater than absolute value of t sub 0, right? So that's how we find the p-value for a two-tailed test. So in this case, that would be 2 times the probability t is greater than the absolute value of this. So it would be t is greater than 0.013. Okay? And we know that which means yes, we want to find the area to the right of 0.013, and with the degrees freedom, we have the degrees freedom is -1, which is 45 minus 1, which is 44. Let me see if I can get the t-table or not. Let me see if I can get the t-table or not. Okay, it's not over here. Just keep the numbers in our mind. 0.013 degrees freedom, 44. Where is it? This iPad. T-table is over here. So it's something like that. So we know the degrees freedom is 44. We don't have the 44 over here, but we want the area in the rectangle. Oh, we want the t-square is 0.013, so 0.013. Let me take a look at it. If I can 44. So we don't have 0.013 over here. We got degrees freedom over here, and we got the area in the rectangle 0.01. T-square. But we can tell that the probability will be greater than 0.5. Why was it? Because we know that we are looking for the probability t is greater than 0.013, right? 0.013 is in the first column here, 0.013. So for the degrees freedom 44 is somewhere between 40 and 50, right? And we know that the t-square should be 0.013, so it should be on the left-hand side of this 0.68. The corresponding probability is 0.25, which means we cannot find the exact the probability from t-table, but we can find a interval. We can find an interval. Let me go back to that. So we know that based on what we just saw from the t-table, we have that the probability t is greater than 0.013 is definitely greater than 0.25, right? We are not able to find the exact p-value or the probability from the t-table over here, but we are able to find an interval. So this is greater than 0.25, so 2 times that, this would be greater than 0.5. If it's greater than 0.5, then it is definitely greater than 0.05. Okay? Now we have p-value, greater than alpha. So conclusion, fail to reject. Fail to reject the null hypothesis. There is insufficient evidence, I'll put it over here, to support the alternative, which is mu is not equal to 5, 7, 1, 10. Okay, so basically, let me clean this here. The whole thing here. So basically, if you do the calculation by your hand, and that's what you want to show me to get the full credits, okay? The first step, non-alternative, the value of alpha, and then test statistic, and then p-value. So if you want to find the p-value from the t-table, sometimes you are not able to find the exact value or the exact p-value, but at least you can find the interval like what we just did over here, okay? So if you have any problems with how to work with the t-table, you feel free to email me or just come to my office hours, okay? And then, since in this case we have p-values greater than alpha, so conclusion, we fail to reject the non-hypothesis. So there is insufficient evidence to support the alternative. So that's if you have a TI-84 or TI-83, you can find out the p-value from the calculator directly. So you can skip this test statistic part. Okay, you can skip that if you are able to find the p-value from the calculator. Okay, but if you want the calculation by hand, you gotta show me this step over here. And this the whole thing you need to show me if you want to get the full credits. All right, just let's take a look at solution here. I think it's pretty much the exactly same thing as what we just did. So since it says that since the sample size is large, because n is equal to 45, greater than 40, so we follow steps for testing hypothesis tests about population mean for large samples. And then step 1, the non and alternative. So it's this two-tailed test. Step 2, alpha. And step 3, we got to do the test statistic t sub 0 by applying the formula we went over above. And we get the t statistics is negative 0.013. And then, so since this is a two-tailed test, the p-value is the area and the t-distribution with a -1 is equal to 44 degrees freedom to the left of a negative 0.025 to the left of that, which is equal to negative 0.013, and to the right of 0.025, which is equal to 0.013. Okay, and what we just did, we are not able to find the exact value of the p-value in this case, but we can get an interval. This is greater than 0.5, of course, which is greater than 0.05 as well. So since p-value is greater than the level of significance alpha, 0.05, we fail to reject non-hypothesis. And then solution, there's insufficient evidence at the alpha is equal to 0.05 level of significance to conclude that the mean RMR of males listening to classical music differs from 5710 kJ per day. So that's pretty much the solution of this example, and you will see a video of how to find the p-value from the calculator separately. That's the example 1. Let's take a look at the next example here. So this example says, according to the United States, mean quarters weight 5.67 grams. A researcher is interested in determining whether the state quarters have a weight that is different from 5.67 grams. So he randomly selects 18 state quarters from a normal population with them and obtains the following data. So in this case, since we have the sample size is 18, which is less than 40, right? But we have that is coming from a normally distributed population. So we just it is okay to do to follow the regular steps to do the hypothesis test. So what we're doing here, since we don't have the, do we have that? Let me see. Yeah, since the problem gives us the raw data here, and I'm gonna show you how to find the p-value, how to do this kind of hypothesis test from the calculator in a separate video. Now let's just take a look at how to figure this out by hand. So we get a bunch of raw data, which we get 18 different numbers. At alpha is equal to 0.05 level of significance, is there evidence to conclude that the state quarters have a weight different than 5.67? So what kind of test we're doing here? First of all, we're doing a two-tailed test, and then let's take a look at what it's saying here. Since the sample size is small, we must verify the data come from a population that is normally distributed with no outliers before proceeding to steps 1 through 5. So we know that it's coming from normally distributed population, so we just follow the regular steps. So step 1, the non and alternative mu is equal to 5.67, and since it's a two-tailed test, so we have mu is not equal to 5.67 in the alternative. And then the level of significance is alpha is 0.05. Step 3, from the data, the sample mean is calculated to be 5.7022, and the simple standard deviation is 0.04797. So of course we have the x bar is equal to sum of xi over n, and we have the simple standard deviation is equal to square root of sum of xi minus x bar squared divided by n minus 1. You gotta be really careful if you do the calculation by your hand. Since you're calculating the simple standard deviation, you gotta divide n minus 1 down here. Okay, of course, if you have a calculator, you just need to type in the data in the stats, in the list, in the stats, and you don't have to calculate the simple mean or simple standard deviation separately. But anyway, once we get the simple mean and standard deviation, we just need to apply the formula. This is x bar minus a mu sub 0, and then divided by the simple standard deviation over square root of n, right? Simple standard deviation is 0.0497 divided by square root of 18. And if you type the whole thing in your calculator, you have this is equal to 2.75. And of course, since this is a two-tailed test, and the value is the area under the t-distribution with n minus 1 is equal to 7 degrees freedom to the left of negative t sub 0.025, which is equal to negative 2.75, and to the right of t sub 0.025, which is equal to 2.75. So if you go to the t-table, we will have the sum of those two probabilities will be somewhere between 0.01 and 0.02. Okay, since the p-value, so whatever the exact value of p-value is, it is between 0.01 and 0.02. It is less than alpha, which is 0.05. So since the p-value is less than alpha, we reject null hypothesis. So there is sufficient evidence that the alpha is a 0.05 level of significance to conclude that the mean weight of state quarters differs from 5.67 grams. Okay, so once again, I wouldn't show you how to work with the t-table again because it's very similar to what we just went over above here. So the main difference here is that it gives us a raw data set here. So we need to, if you want to do the calculation by hand, you need to calculate the simple mean and the simple standard deviation separately. All right, I think that's pretty much all about this part, and feel free to let me know if you have any questions. Just email me or come to my office hours. All right, that's all about this part.